Okay. That look about right. So the three sections, you guys are well ahead of everybody. So everybody else is just getting into lipids, so they still have a little bit of three to clean up. So you guys are a little bit ahead of them, right, by at least about an hour or so. So let's take a look now at the next one. So we just finished up three, right? So we're talking about macromolecules. Now we're moving on to the next level of organization, right? So we started off with atomic, molecular, macromolecular. Now the next level is going to be organelles, right? And then of course organelles and cells. So we basically pull that together. And that's kind of what this chapter is, right? So we're looking at the cell structure. We're basically looking at the organelles associated with this particular system. Now, let me go ahead and kind of take a little bit of a walk back and a kind of a little bit of a historical view of things, because, well, I'm all about history. So first of all, we're going to talk a little bit about some of how we kind of came to the knowledge that we came to, and it all begins in about the 17th century. So around the 1660s-ish or so, there's a couple of things that happened here. Obviously, Robert Hooke discovered the cells, but right around in this area, the way he discovered cells was that the invention of the microscope was also happening around this time. Anton van Leeuwenhoek, who was just an inventor, that he finds his way into science textbooks, not because he was a scientist, but because he was an inventor. Basically makes his way into textbooks because he invented probably one of the most important biological tools ever. And that's basically our microscope. Now, during this time, Robert Hooke, who's kind of considered the father of cell biology, kind of began that entire branch. But unlike these days, where you kind of start to have a new discipline emerging and it takes maybe a decade or two to really fully come into its fullness, this took a few centuries to come into its fullness, and mostly for a very good reason. Because the invention of the microscope was kind of one of those watershed moments in science, where it sort of turns the way we see the world upside down, right? And sort of kind of grasp a way of what this meant to society. This happens every now and then, by the way. The history of science is punctuated by moments that basically alter reality for society as we know it. This was one of those. Obviously, evolution in the 19th century was another one of those. Nuclear physics, in particular the mushroom cloud, was probably the most recent of those. And so these are like watershed moments. So like it cuts society into sort of the before and after. It's like our reality is never the same again. And in particular, this is like one of the very first ones that really kind of just scrambled our squash. And here's what I want to paint for you what life was like then, so that you kind of get an appreciation, because a lot of times we kind of take things for granted, right? We take all of our technology, which is life altering, and we just sort of get used to it and get to expect it, and then we kind of get pampered by it, and then we get spoiled by it, and then we become mostly useless without it. But we largely forget like what it was like to not have, say, for instance, a cell phone. Okay. And so this is kind of one of those watershed moments. It's actually worse, to be quite honest with you, because this was not just a gadgetry. This didn't just increase your productivity, which is all technology does. It just allows you to do the same things you've always been doing, but it allows you to do it faster and more efficiently. That's all technology does. So it's really not all that earth-shattering. Even if you take the most amazing technological gadget you could think of, like the cell phone, for instance, fully endowed with apps, which came out for the first time with the iPhone, first generation iPhone. I mean, that was like a really revolutionary piece of technology that sort of changed generations from the haves and the have-nots, right? But even then, that wasn't as earth-shattering as this particular event. This is like if you want to put it on the Mount Rushmore of like scientific moments that altered humanity, this is like one of the biggies. Right, this is Washington looking forward and leading everybody else behind him. This is one of the big ones, even bigger, I would argue, than evolution itself. And here's the reason why. Because up into the 17th century, just to kind of paint a picture of the way the world was back then, this is an area of humanity that we refer to as the Baroque period, right? I mean, Bach was alive here. I mean, he was a rock star at this time. Vivaldi, if you're into music, Telemann, all those sort of Baroque-ish types of, they all sound the same, right? So those guys were a thing back in then. This was well before the US, right? This is, you're kind of in the 1660s, you're talking probably about Jamestown-ish era, right? When we were largely kind of colonizing in this country, but mostly dying and not surviving, right? So you're talking about the very, very beginnings of us actually coming over here. And this is what was happening in Europe. But what you have is really a view of the world that, for the most part, is dominated by philosophy and probably even more so by theology. So in the 1600s, you're kind of coming out of the Renaissance period, which was sort of like the reawakening out of the Dark Ages. The Dark Ages, by the way, were dark for a reason. It's because we basically got so stupid that we had to relearn the things that prior civilizations had down, right? There's a reason why they have this whole era called neo-classicism, because we had to go back and relearn what we forgot, right? I mean, it got dark. I mean, basically life was all about just surviving to the end of the day. That was it. That was your life's goal. I just got to live today. However I do it, however many people I have to kill, however much bread I have to steal, I just have to live to see the end of the day. And that was it. That was your life's ambition. That gets pretty dark. You don't have a lot of room for academics if that's the case. But guess who does? Not normal people, because we're busy basically fighting and striving to stay alive, right? Who does have time and money to learn academic pursuits? Yeah, the nobles, right? Which in this era, largely if you were a rich person, you were a royal of some sort. There was no such thing as self-made millionaires. They didn't exist. This was, we didn't have merchants. We had rich people, and we had people who pretty much licked the bottom of the boots of the rich people, right? That's pretty much what there was. There was no middle class. There was no merchants. There was no self-made millionaires. The only money out there was inherited money. And so you either were very, very useless because you had so much money that you were pretty much useless to humankind, or you had nothing and you were also useless to humankind because you were too busy just trying to live. And you didn't have anything in between, right? These were very, very desperate times. There's a reason why entire revolutions were born in these times. Hello, I'm talking to you, French Revolution, right? Right. There's a reason why the Americans basically handed it to the British, is because of this, right? This sort of haves and have-nots idea. This was the reigning idea, the reigning ethos of the day. And so ultimately, then in this particular time period, most of what people had to hold themselves together was theology. This was the reign of the Catholic Church. This was the Catholic Church, and for all of its positives and negatives, in the West, obviously, because that's where the Catholic Church was mostly active in the West. The East, totally different history, totally different kind of historical timeline going on, and from the Middle East to the East to China and things like that. Completely different trajectory of history. Mostly this is a Western type of style of history, the Dark Ages, right? It was dark for the Westerners, not for the Easterners, right? But what held Europe together in those desperate times was the Catholic Church, right? Was, even though I've got my sword to your throat, we were both Catholics, believe it or not. And that's kind of, that meant something, right? At the end of the day, and that's kind of what held society together. So what you really had was the Catholic Empire during the Dark Ages. That's kind of where you still are when you come to the 17th century. Now, why is that important? Because notice what I didn't mention. I didn't mention any of the big three, right? In the beginning of the semester, we talked about three schools of thought, yes? Three intellectual disciplines. We talked about philosophy, we talked about theology, and we talked about, which is mostly the scientific view of the world, right? Notice that one doesn't even exist in the 17th century. And most of what you had was philosophy, which held together the ancient world, Greek philosophy, Roman philosophers, things like that. That's what held together Rome, the older societies. But then after the growth of the church and Catholicism and the spread of Catholicism throughout Europe, then that kind of replaced philosophy as sort of the glue that sort of held common countries together, even though they were interestingly at war with each other. It's just a lot of paradoxes in that time. I don't really know what quite it meant to be a Catholic actually back in those days, but so it was just an interesting, totally different world. But you didn't have any science. There was no scientific thought. There was no scientific reasoning. There was nothing. I mean, you had a little bit of rattling around with some of those astronomers, right? Copernicus was kicking around, also got into big trouble for it. All of those Kepler, I mean, all those astronomers that you study about in astronomy, they've been doing their thing, but they've also gotten a lot of trouble for it. Who did they get in trouble with? The Catholic Church, right? But this is kind of what you have. This is the what's holding society, for good, for better. I'm not saying it's good or bad or any different. It's just what we had at that time to hold us all together, just like science now kind of holds us all together now, right? And so that's kind of what we had there. But along with that, because you didn't have anything like a microscope, you also had this perception of reality that was limited. So for you living in this era, in this time, you didn't have any perception of reality beyond what you could visibly see. Like nothing. Like even if it's really, really tiny, it's like, oh yeah, I can see it, so therefore it is. But to basically say it's like, oh, well, there's this thing called a bacteria, which you guys have all seen already, right? Because remember that lactobacillus, I had it set up. You guys saw it, but you can't see it, can you? It's on you right now. Right? Forget it. It's still there. You're just wiping it on this hand, right? So there's more of them than there are of you. But guess what? You can't see that, so it didn't exist. Back in this day, there was no way to even look at this or to even imagine that this existed. Not only that, but even worse than our society now is they didn't even have an imagination of something like this to actually occur. Like they had no concept. Like now we have science fiction writers that can kind of explore and sort of set up different alternative realities, and we can kind of like dig into that a little bit. They didn't have that. They didn't have science fiction. There was no science. So they had no concept whatsoever and no imagination at all that anything smaller than the naked eye could ever exist. So that was their reality. Then comes along this Dutch joker who invents a series of lenses that instead of making planets look bigger, makes objects appear out of nowhere. Now all of a sudden you're looking through this microscope and you see all of these little things, bacteria in some cases, cells more likely in others. And all of a sudden you can see stuff that you never saw before. And so now when I'm looking at a tabletop, it's not like there's nothing there. There's something there. Well, guess what? Guess what just happened to you? You basically just had your entire reality turned upside down. Yeah, literally, right? And not only that, but it's even worse than that, right? Because even if you looked at it with your own eyes, you'd be like, whoa, there's like all this stuff here. I can't even see it. This is like craziness, right? Where'd this come from? It's like you're looking at it and you're looking, there it is, it's gone. There it is, it's gone, right? So, I mean, you're like trying to talk yourself through. It's like, am I crazy? Am I seeing what I think I'm seeing? Am I hallucinating? Right? So you're seeing all of the, what kind of witchcraft is this? You could imagine this, right? I mean, people getting burned at the stake or thrown in dungeons, this sort of thing, right? I mean, you can almost imagine that happening as you're sort of first seeing these first cells for the first time. And yet there they are, but you're still trying to grapple with it. Why? Because everything that you were taught from when you were little all the way up until you're an adult basically was wrapped around a reality that assumed that there was nothing that existed beyond your visible range. And now we're trying to say that everything you knew to be true is not. That is like a mind-melting moment. None of that, but remember, you're talking about a society also that's held together, at least in Europe, that's held together with theology, right? I mean, we are we identify with each other in a lot of ways with each other through like religious connections or theological ideologies with each other. That's how we're relating to each other in a lot of ways, when we're not killing each other, right? So then not only that, but then there's nothing in theological literature that prepares you for the unseeable. So like, according to the church's dictum, they would say, listen, this isn't real. This doesn't exist because that, you know, what we have is what we can see. And yet here it is in front of you. You can see this. So you can see it's not just turning your sense of reality upside down, but there's all these things that you can't see that actually exist, but it's also turning all upside down all of your theological concepts of what's real and what's not, and how do you redefine reality, and how do you make that mesh with the, does that sound familiar? Did not evolution do similar things to theology, where it kind of turned your conception of how everything fit together upside down, and now you're trying to figure out, well, this is what it is. I mean, this is kind of what we see. Now, how does that all fit together, right? So you can see similar types of contortion. So this was a big mind-melting moment in this particular area. And basically, they for the first time, they kind of saw something that they never even perceived or believed was actually true. To give you an idea, to grasp, help you grasp what we're talking about here, let's do a similar sort of a moment for us here. Only in this case, what I'm going to do is I'm going to make an invention, just like Van Halen did. In this case, I'm not going to invent a microscope. I'm going to invent a pair of glasses. But they're special glasses. They're ghost glasses. So without them on, the room looks empty. Put those ghost glasses on, and you can see everybody walking around. Kind of like the Haunted Mansion at Disney, right? So now think about this for a second. We're not just talking about the occasional ghost wandering down the hallway, all aloof like. What we realized in our discovery of ghosts is that they're not just sort of walking back like this, you know, not really paying attention to you. No, they're like trying to talk to you, right? They're like all in your face. They're like, right? So they're like pepper spray territory, right? That's what they're like. They're trying to talk. They're trying to talk to you. And not only that, but it's not an occasional ghost. Think about this for a second. How many people have been on this planet? There's 8 billion-ish plus on here now. There's been hundreds of millions in the past. We're not quite sure how many, but a lot. If we factor that maybe 10% of those lost souls get stranded wandering around the corridors of the earth, that is still a titanic number, yes? So we're not talking about a room that's mostly empty. We're talking about a room where there's actually probably more of them than there are of us. Especially if you happen to, you know, live somewhere or on where they built over one of those cemeteries. Right? I'm looking at you, Cheeseman Park. But anyway, right? I mean, yeah, there's a reason why you don't do Halloween on that park. But anyway, right? So you have a lot. Oh, but guess what? They're not just here. They're at home too, aren't they? Yeah. So think about it. You get up in the morning. Let's just see how altering this is for you guys. So some of you guys are like, hey, this is cool. This is awesome. Is it? Think about this for a second. Let's imagine that you get up for the day and you want to go in the shower. And you walk into the shower, you strip down and you buff, right? Oh, but wait. Let's just try the ghost glasses. You put them on and it's like, oh, whoops, sorry, you got somebody sitting on the john. The other guy over here brushing his teeth. There's somebody in back of you, not quite sure what they're trying to do. There's 3 people in the shower. And they're all looking at you. They're all like, right? So it's creepy. How long is it going to take you to put those clothes back on? Yeah, you'll pass, right? I'm a little ripe, but you know, as long as I stay downwind, I'm okay for another day, right? Bathing habits would change a lot, wouldn't they? Oh, no. That's easy. That's easy. Let's imagine it's Valentine's Day and you go out with your significant other and you have planned a nice, quiet evening with Barry White, some wine, turn the lights down low, spend a little intimate time with your significant other. So, of course, you retreat to the love parlor, better known as the bedroom. And of course, one thing follows after another. You get the picture, right? Oh, but wait. Hold on. I got to do this. Let me put the glasses on. Just do a quick scan. I mean, I'm already like in my J suit, right? So I'm already there. Just in case, right? Just let's put it on. Oh yeah, and here, there's a guy right standing next to me, just like watching us, like, right? There's another guy in the bed like this. And Uncle Charlie's sitting right there. It's like, Uncle Charlie, you died like 5 years ago. What are you doing here? Is that a showstopper? Yeah. Did we just call the night to an end right there? Yeah.
Charlie alone.
Yeah, Uncle Charlie just by himself, right? You know, all the other voyeurs, you're like, okay, great. This is what I've got to deal with, right? I mean, that's a showstopper. The birth rates in this country are going to go way down. But think about it. How's that going to affect you? Are you ever going to feel comfortable again? Stepping into the shower, knowing you're stepping in there with a whole bunch of other people checking you out that are all dead, so you can't get rid of them. Having a relationship with somebody, knowing that there's not just another person in the relationship, there's like multiple people in the relationship. Oh, how about this one? What about if somebody was like a widower or a widow and they get remarried and it's like the ex-husband is there? It's like, whoa, okay, this is not what I signed up for. But he's there along with his dad and his grandpa. I mean, the whole family's there, right? I mean, it's like, okay, this is like, no, I can't do this, right? Would you always be looking over your shoulder? Would you always be looking at an empty room wondering, who's in here? Would that change the way you do things? Would that change the way you think about your life? The way you live your life? Yeah, your life would never be the same anymore, would it? It would be like a before and after. It'd be like the Matrix, right? You took the wrong colored pill, right? That's exactly what happened here. This is a moment that changed everybody's life. The reason why it was so slow in changing was because most of us were busy fighting desperately to get a scrap of bread. We didn't have the kind of useless time that these aristocrats had to spend playing with a toy, which was literally what it was. Which, by the way, if you're wondering, is the reason why scientific literature is littered with rich, white aristocrats. Wait, let me modify that one. Rich, white, male aristocrats. Because they were the ones who had the money and the extra time to be able to do these sorts of things. Back in the day, believe it or not, when you were a noble back in this time, you really did one of two things. That's it. You were useless otherwise. You did one of two things. You either fought wars with each other or you did some sort of an academic pursuit. There was really no in between. So that took a long time, right? So this microscopic invention was kind of like the fad toy for the glitterati for like a long time. It's like everybody had to have one, right? It's kind of like the new fad app, right? Angry Birds, right? Everybody's got it on their phone. And now there's like what, 500 million different knockoffs of Angry Birds. But basically it's like everybody had to have one. And some of these rich people were just useless. They were just like, oh, hey, isn't that cool? Look, I'm rich. I've got a toy. That's great. But some actually took it seriously. And they actually, and those are the ones that we read about in scientific history, being like, this guy is the one who did this and Lord this and that sort of the other thing, right? Because they actually took the time not to just be rich and stupid, but they actually tried to be rich and smart, right? They tried to learn something about this. They're like, well, wait a minute, this is really unique. And I understand what's going on here. So what does this mean, right? So what they started doing is they started writing stuff down. They started drawing pictures of what they were seeing. They started sketching and recording what they were looking at. And this happened. And Robert Hooke was one of the first ones. He was one of the first ones who actually took a look at this, and he actually coined the term cell from cork, actually, because each of those individual little circular units in cork is a cell. And then you notice that the cells in the microscope look very similar to that. So he called them cells. That's where the term comes from Robert Hooke. That's why he's called the father of cell biology. He's one of the first serious people to really take a look at some of this stuff and try to make sense out of all of it. And then you had hundreds of years of observation after this. Notice the time spread. You're going from the 1600s to the 1800s by the time we actually settled it all down and turn it into something. By the way, we make a lot of fuss about the 20th century. A lot of fuss. We're making even more fuss about the 21st century, right? That's just because that's just the way we are. But don't sleep on the 19th century. The 19th century was actually a more critical century than probably any other century before. Because the 19th century was kind of like, if you look at it kind of an agricultural analogy, the seeds that were sown in the 19th century became the massive blossoms of the 20th. So if the 19th century hadn't been sown scientifically the way that it was, then we would never have seen any of the progress and the advances of the 20th century. So we oftentimes look back in the 20th century, we're like, wow, look at our amazing technology and all the advances that we had and all that sort of stuff. And all that's true. But we oftentimes look at that and be like, well, look at these like pathetic 19th century people. They're, blah, blah, blah. It's like, no. You don't diss on the seeds, because without good seed, you get no blossom. And that's what was being sown in the 19th century. You'll notice this. I'll point this out actually very clearly to you guys. This is one of those really titanic seeds that was sown scientifically, oftentimes overlooked, oftentimes not considered with its full importance. But this is what happened. So after 200 plus years of observation of cells, two cell biologists in the 19th century, Schleiden and Schwann actually has a cell type named after him in the nervous system, pulled together what we now know as the cell theory. And notice this is like mid 19th century. So if you're just keeping track in terms of the US, in the 1830s, this was before the Mexican-American War. This was before the gold rush of California. Okay, so California wasn't even part of the Union here, still Mexican territory at this particular point. So that's what was happening in the US. That's when Schleiden and Schwann was pulling all this together. But basically they proposed the cell theory. And so what is the cell theory? So what they did is they basically took all the observations over centuries of observation of all those who recorded their observations, and they came up with three basic components of the cell theory. Now, the cell theory is inductive reasoning. Remember that one? What was our example of inductive reasoning in chapter 1? Something you guys all know. I had you guys go outside and tell me what the color of. Yeah. So remember, everybody agreed it was blue, right? Why? Because they did experiments on it? No. Because over millions of observations, you've never seen the alternative. That's inductive reasoning. The same thing holds true for the cell theory. So the cell theory are basically conclusions that we come up with, just like the sky is blue, that are true because of multiple observations over hundreds of years of observations. We've never seen the alternative be true. What's the first one of those? All organisms, that is to say, all things that are alive, are composed of cells. If we can define it as living, it's composed of cells. Now, that's not an easy thing. I mean, throughout scientific history, that was actually a very long and protracted, difficult and painful growth process. Just simply doing something as yeah, duh to us now as, is it alive or not? Right? I mean, what, most 2-year-olds get that one down now? Well, back in the day, we had entire professionals who were struggling with that. Because even though there were things were obvious, right? So for instance, are we comfortable with us being alive? How about a dog? Yeah, right? It's similar to us, furry, ears, cute, right? That kind of thing, right? So we're okay with that one. What about a plant? Are we comfortable with that one being alive? Oh yeah, but wait. It doesn't fit your criteria. It doesn't have ears, doesn't have fur, doesn't walk around like we do. So, but it can die, right? So there is a very sense of like, this is alive and this is not alive. So therefore it must be alive, right? Well, let's keep going. Let's go to like, algae. Is that alive? Oh, we'd say yes now, right? Because we know better. But think about it. You see this kind of like green slime. And back in the day, you're having a problem with this, right? Is it alive? Does it move? Doesn't have ears? No fur? Does it have a clear life death pattern? I mean, what does it look like when it's dead? I don't know. It's just kind of green slime all the time, right? Is it actually alive? Right? That's not so easy now. How about a rock? Is that one alive? Well, let's look at it. Doesn't have ears, doesn't have fur, right? Does it live or die? What if we break it? Is it dead? No, we don't think of it as dead. We just think of it as smaller, right? So you can see that that wasn't a gimme. There was a whole process because we'd never thought about this before. Think about it. We were coming out of a society that was largely held together with philosophy originally, and then theology most recently. And now we're emerging out of this sort of theological backdrop. That's what our education, our training is in. And so when you think about it, the theological and the philosophical perceptions of alive and dead are very different than the scientific, right? Because being alive has all these other sort of supernatural connotations to it and stuff that we know. I mean, and that was mixed in here, right? So it's like, oh, well, we have a soul, so therefore we're alive, right? And that's kind of a theological construct. And we can kind of extend that. It's like, well, animals kind of have a soul. And then there's a big debate about that one, right? So it's like, well, they kind of have a sort of a dog soul to them, right? And there's kind of a, right? And then plants, it's like, well, plants don't have souls, so therefore they're not alive. But they are, because they have a life and a death cycle, right? So now you're kind of trying to slowly separate kind of your theological perception of life in trying to replace it with something else. And it took a long time to do that, which is the reason why some of this took hundreds of years to develop. But what we ultimately noticed, once we finally settled on a sort of a very strict scientific version of like what is living, we noticed that anything that scientifically we feel comfortable with being alive is actually composed of cells. And now it's basically to the point where it goes the opposite way, where we can say it's like, we're so strong about this one that we can actually say, even if we don't know what something is, like if we don't know if it's alive or not, if we see cells in it, then it was alive. It's alive. Okay, so it actually becomes predictive. That's an inductive reasoning. That's an inductive conclusion that gets so strong that you can start to predict. You're so convinced of it that you're willing to put money on the table for it. Okay. The other one is that cells themselves are the smallest living things. That is to say that these guys are the basic unit of life. What does that mean? This is the smallest we can get. And still answer all the big biological questions of life. right? Just like the atom was the smallest unit of matter, this is the smallest unit of life. So if you get smaller than a cell, you're not alive anymore. And then there's this one. The cells basically come from other cells. Okay, wait a minute. How many of you guys are looking at this one? You're thinking, well, of course, like duh. Like where else would they come from? Like a peanut butter jar? I mean, right? But think about it. Where do puppies come from? Yeah, right? Where do kittens come from? Where do people come from? Babies. Yeah, right? So it's like, okay, where do cells come from? I'm like, where else would they come from? Right? Is it that kind of a yeah, duh sort of a thing? It seems like it's a yeah, duh now. But there's a couple of issues going on at this particular point in the 19th century that made this one critical. First of all, you need to understand something very clearly. This is pre-evolution. Darwin didn't publish his work until 1859. So we've got a couple of decades before Darwin comes around. As a matter of fact, I believe at this particular point, he had just finished his Beagle trip and he was largely in his whatever lab or whatever, and wherever he was, just trying to make sense out of everything. So this is kind of the dark days of Darwin when he was trying to make sense out of everything, sort of pulling everything together. So that wasn't really even a thing. That wasn't even on the horizon. If you're just wondering, some of the components that factor into current evolution, like the geological components of old Earth and those sorts of things, which is kind of like a split oftentimes between the theological perspective and the scientific perspective. Some of that had already been coming together in geology through Lyell. And there was actually even some denominations, some religious denominations that were also espousing kind of an older ancient Earth type of a theology framework. And those were kind of those are sort of percolating in the background. So Darwin did not come up with the old Earth concept. A lot of times people think he did. He didn't. That was mostly geology that did that. And actually, interestingly, some of the some divisions of I don't know which particular organization it was. I don't know if there's a Protestant organization or something like that, but there's a couple of them in there that proposed the potential for an old Earth type of a paradigm, even before all of this. So that was kind of percolating in the background, but evolution had not been a thing. So we didn't have any concept of natural selection. We didn't have really any good idea about, species, how they adapt, or any of the things that we take for granted now. None of that was there yet. And so what was there, however, was this idea called spontaneous generation, which we'll talk about again when we get to the genetics chapter. But spontaneous generation was somewhat farcical. I think you guys will probably chuckle when I mention it. But spontaneous generation was the belief that non-living things can give rise to living things. Let that sink in for a second. Non-living things could give rise to living things. That's what spontaneous generation said. Like, for instance, a rock could transform into a living thing. Now, does that sound a little kooky?
Yes.
Oh, it does to us now, but not back then. So even in the 19th century, when we're starting to learn some things, actually spontaneous generation was very persistent. Matter of fact, it was extremely persistent. And it actually took Louis Pasteur of pasteurization fame, the father of microbiology, the one who actually had to create sterile technique, by the way, which many of you have been practicing during COVID, right? When you are washing your hands obsessively until they basically turn into dust. When you're minding your high contact surfaces and you're wiping things down to minimize viral transfer, all of that is part and parcel to sterile technique. Louis Pasteur had to create that in order to finally debunk spontaneous generation. Kelsey.
So he knew that you could
He didn't necessarily know because we didn't have good enough microscopes to see bacteria. But what he did notice was the potential for contamination. We didn't really understand necessarily all the ins and outs of it, but he did realize that there's potential for contamination and that you need to really kind of eliminate sort of contaminating influences by going like ultra neat, right, basically. So I don't know that he understood bacteria quite as well as all that. So, but he did know that there were some things in the microscopic world that were potentially contaminating, or in the subvisible, not even necessarily microscopic, right? Because fly eggs are not microscopic, they're subvisible, but they're not microscopic. I mean, if you like use just a magnifying glass, you can see fly eggs, right? But they're just very tiny. So just that idea of like, well, if you let flies crawl over your meat, that's not sterile anymore because it's dirty, right? So the idea is if it's just the meat and only the meat, there's nothing else that ever touches it, breathes on it, looks at it, or anything, then there's no source for any outside interference. That would be an absolutely clean environment. That's the way he saw that, right? Not necessarily like, oh, well, yep, there's a bunch of bacteria right there, and you got salmonella over there, and you got listeria over there. No, it wasn't any of that. We didn't even come up with that until well into the 20th century. But we knew, at least at this particular point, we knew that there was something in there that was causing a problem, and it needed to be sort of treated differently. The meat did anyway. No, but this is what this is going after. This is basically saying to all those spontaneous generators that cells come from other cells, hello, not a rock. Because if you think about it, that makes sense. Because remember, you don't have a good grasp on the microscopic world. So for you, if you see a piece of meat that all of a sudden starts to grow worms, it's a natural question. Where did it come from? I don't know. Did you see any worms crawling up to it? No. Right? Of course, you don't know enough biology to connect the fly that's crawling on it with its reproductive cycle of laying the eggs. You don't know any of that. There's none of that entomology is there, right? So it's kind of like it's a reasonable argument based on ignorance. Not a bad type of ignorance. It's just we hadn't learned that yet. So it's very reasonable, which is, and the reason why I love to use spontaneous generation as an example, as a cautionary tale to all science, is beware when you think you've got it all down, because there's always a certain amount of ignorance in what we don't know. And when we think we've got it all just right, then oftentimes we'll get some results that turns everything upside down. Why? Because we had a reasonable explanation for it, but it turned out to be wrong. Why? Because we didn't know something that was critical. Right? So that's basically what this is saying. They're saying basically you have to come from pre-existing cells. You can't come from a rock. And that's kind of what they were driving home. Not only that, but whenever you're looking at something like that for the first time, and we're doing the same thing, by the way, with astrobiology, right? We're out there looking for things. And if we find something, yeah, we have a lot of information on how things work here. But I can guarantee you they're going all the way back to the same level. They're saying, listen, I know how it works on Earth, but we can't make the assumptions that it's all going to be the same if we find life on Mars, right? Because there could be variables associated with Mars that don't exist on Earth. And they could have a radical different pathway and a different way of doing things than we have here on Earth that we haven't considered because we've never encountered Mars. It's a new system for us. I can guarantee you in astrobiology, they're doing the exact same thing, right? They're dialing it all back and they're saying, yeah, it's a yeah, duh question, but it's not really, because you've got a completely different system and you have to start from scratch. Pretend like I know nothing and start over, right? That's how you have to start. So this kind of gives you this concept, and then it was within this context then that also sets up another piece for what Darwin gets to eventually, right? Which is this idea. So not only do you have kind of like some of this old Earth stuff rattling around in geology and some different theological regions are also kind of kicking around that potential idea as well. But now you've got these guys who say that that other cells come from pre-existing cells, like mom and dad cells give rise to baby cells, which just like with us creates a descendancy, right? So that we have a line of descent that we can trace all the way through our family tree. A lot of times the royals do it quite well. I mean, people in this era, these days, they do it a lot. we don't really do genealogy a whole lot now these days. Mostly because if you're like me, you're just an average guy. There's really nothing interesting there. So it's not like I'm not gonna inherit anything anytime soon. I'm not gonna, I'm not a prince anywhere. I'm just an average schmuck, just trying to stay alive, just like all the rest of us. So it's not like I have any reason to look into it other than just like, oh, gee whiz, that's kind of cool. But back in those days, in these days, it was a big deal, right? Because, I mean, if you were descended to a royal family, then you could have some claim, there could be something coming out of it. It'd be like winning the genealogical lottery, so to speak. I mean, so they were much more interested in that sort of thing in this particular era, in this day and age. But what this did then is it kind of set up this concept that then would be leveraged in Darwin's work 20 years later about this concept of a single line of descent. In this case, not from one cell to another, but from one organism to another. And that would be one of those things which actually kind of sets up in a lot of ways the very fascinating sort of view of Darwin. If you take a look at this idea of descent, if you're talking about descent, what discipline of biology are you talking about? Yeah, which is genetics, right? Darwin oftentimes said descent with modification, right? So you kind of change a little bit every generation, you get a little bit better, and then eventually you turn into like a super rabbit or whatever. But you kind of get better and better at what you do, you can adapt to your environment, those sorts of things. But this is kind of one of the things that's so fascinating about the entire evolutionary concept, is because when it first came out, it was really kind of, I don't want to be too negative on it, but it's kind of philosophical in a sense, because we didn't really have a lot of good, robust science. And we had a bunch of bones and rocks, but I mean, whatever, right? I mean, all that really tells you at the end of the day is a bunch of dead stuff that's not alive now, right? And I mean, there's a lot of stuff that we tried to do with that, but it was always kind of thin and it always fell short. But this is the reason why I love the genomics era, because now for the first time, we can basically go back and say, listen, what this guy wrote in 1859, it was never about fossils. It was never about rocks. What he was writing about was about genetics. And now that we have genomics, we have entire genomes sequenced. Now we can actually take a look at all of this the way it probably should have been looked at from the beginning, is not through the hazy lens of a bunch of dead stuff and rocks. You can see I'm not a big fan of fossil record. I'm not a paleontologist by any stretch of the imagination. I'm more of a genomic person. But we can look at it through descent. If the way an organism, the way a species adapts and turns into other species in its environment, if that is a genetic thing, then you have to study the process from a genetic lens. And this is the first generation when we've ever really been able to do that in a significant way. This is one of the reasons why the last Nobel Prize that was awarded in medicine and physiology was awarded to the guy who sequenced the genome for Neanderthals. Because for the first time, we actually have the capacity to genomically study these organisms, in this case, the Neanderthals who no longer exist, and basically study that with respect to, okay, wait a minute, how does this actually look, right? And I don't know if you caught this, but this is the reason why I can't beat this drum hard enough, because most of us see all of this coming together as sort of just an amalgam of dusty things in a museum somewhere, right? Ancient animals that we don't see, rocks that we dig up, sometimes over here, just right up the hill sometimes. But it's like, that's like not even the most important part of it. I mean, the most important part of it is like getting to the actual genome and being able to study from a genetic level how species are changing over time. That's where the fascinating part of it. Now, we can't go back and say like, okay, dinosaurs turned into birds, right? Because we don't have that DNA. Or do we? T-Rex soft tissue, anybody? So you can see why these are exciting times to be living in, because all of our old paradigms are all fossil record based paradigms are all getting turned upside down now. And we're able for the first time to really sit down and study the exact same way that Darwin originally wrote it out. Descent, genetics, over generations with modification. That is a genetic story. And this is the first time in the history of humanity where we can actually do that now. That's why it's so exciting. I'm looking forward to it. I'm looking forward to going to the zoo and seeing the T-Rex exhibit. Not some plastic piece of crap, but an actual real live T-Rex. That'd be awesome. Jurassic Park, I'm in. I'm all in. I may die there, but I'm gonna die happy. I'm okay with that. So, okay. So that's these are important ideas. You notice how this is very important. This is all 19th century, right? I mean, here we are talking about some of the beginning threads being laid down in the 19th century that are basically weaving our reality now, right? The way we perceive reality through all these different lenses. These things were all started in the 19th century. Okay. So now let's shift gears, topic shift, hard shift, actually, hard right, right? Hang on, we're going flat spin. So what we want to talk about now is the cell size, right? One of the big questions we wanted to know is why are cells microscopic? Makes sense, right? Why can't you just make a big one? It's fair enough. It's a fair question. What we noticed was early on, all cells are pretty tiny, right? They're all microscopic. The size of them is limited. So why are they limited? We didn't learn this actually until well after the 19th century, probably more like in the 20th century, we figured out why exactly some of these happen. And as a matter of fact, we're still writing textbooks without this link of knowledge in there. If you've ever wondered, why is a bacteria so tiny, right? Why doesn't a bacteria grow to be the size of Elodea, where you can actually physically pick it up out of the water, take a nip off its leaf off, right? Why is one organism, which is made of cells, bigger than another organism, also made of cells? What controls that, right? Why are those decisions, how are those decisions made early on? These are the kinds of questions that scientists ask, right? Why are these two different? Well, there's one very big, huge component that determines what size you're going to be. Notice what I didn't say. I didn't say you get to choose what size you want to be. I said how you do business determines what size you're going to be. Okay. And ultimately, when you take a look at a cell, a very small cell, a single cell, is only going to be able to move things around within itself by a process called diffusion. So basically, all diffusion is moving stuff into the cell and out of the cell. Very similar to the way we did during COVID shutdown when Amazon saved the world, right? When we basically did all of our grocery shopping on Amazon Fresh, and what they do? They delivered half of your order on your doorstep. And where the other half went to, I don't know, but you got half of it, right? So that's stuff coming in, yes? And of course you have stuff going out. You eat all the food, you generate trash, and you set it on the curb, and the magic trash fairies come by and they pick it all up, right? Only unlike the tooth fairy, they don't give you money for it. They actually take your money. So it's like a mean tooth fairy, right? But the idea is you have a process to bring stuff in for survival and to get stuff out also for survival. The cell's the same way. You got to be able to get nutrients into you so that you can use the molecules that you need in order to build your cell. But then you also need to get rid of the trash. You need to take the trash and send it outside of the cell so that you can get rid of it. Or if you're a group of cells and you're kind of talking back and forth to each other, you got to send molecules out there so that you can send signals and messages to your neighbors, okay? So here's the thing. If you're small, then everything that you're getting in or getting out is by the process of diffusion. So what is diffusion? We defined this in lab, didn't we? The movement of, nope, that's osmosis. Keep going. Solutes, right? From high concentration to low concentration. right? And what was the example we used in the lab? For, yeah, the actual system we used, right? But when I kind of talked it out, I used the example of the food coloring, right? A little drop of food coloring in there, right? And it kind of just diffuses out until you reach equilibrium. Now, did we do the distance thing? Let's do a diffusion experiment right now. I've got a bottle of perfume. I open it up. Who's the first person? First of all, which direction is it going to flow? From the high concentration, which is inside the bottle, to low concentration, which is like all the way back there where Ruben is, right? So the question is, who's going to be the first one to smell it? Well, me. And then, yeah, and then you're next, right? And then you guys will probably be next. And Ruben, maybe, eventually, right? Now, what if you guys, like, we just take it out to the hall here? And instead, let's say I'm going to pick on Ruben because I'm just working on it, right? So let's basically say I send Ruben all the way down the hall, right? Like by where he can see the butterfly. And I've got the open bottle here. Are you guys going to be able to smell it eventually? Is Ruben going to be able to smell it? No, why not?
Because the concentration is already has dissipated enough.
So is it going to get down there? So what would he have to do in order to smell it? Where he's just standing there in the middle of the hallway. Move what? Move closer. So that means that he is too far away. Diffusion, which is exactly what was happening there, moving from a high concentration to a low concentration, is limited by distance. So what does that mean? That means if we are a cell, the only way that we can get business done by diffusion is if we all basically stay within a relatively short distance of each other. If we spread out to the point where like half of the, like you guys are like way down there by the butterfly, that's too far. Am I going to be able to get that perfume to them? No. Now think about it. Let's up these stakes. Instead of just perfume, let's imagine that for some reason, smelling this perfume was a matter of life and death. If you were able to smell this perfume, you live. If not, you die. So what happens to all those who are in close proximity? They live, they can smell it, right? But you guys, right? If you guys are way down the hall, what's going to happen to you guys? Right? You guys will die because you've exceeded the salvation zone, if you will, of the perfume. Okay. Same thing's also true with the cell. Because you're reliant on diffusion, it basically limits your distance, which basically also limits your size. You see this concept, by the way, all throughout biology. It dictates the size of everything in your body. It dictates the way you organize your tissues when you go to build your human body for all of you A&P students, your eventual A&P students. It dictates how big an organism can and can't be. It even goes as far as dictating how big a cancer tumor can become. Because if you outgrow your supply lines by diffusion, then you are no longer able to get the nutrients that you need in order to survive, and therefore you die. Therefore, you're limited in size as a tumor. So ultimately, your access to your supply lines is ultimately going to be what limits your ability to grow in size. So rather than you choosing to be small, what's happened is by choosing diffusion, which is the simplest way of doing things, by choosing diffusion because it's simple and cheap and effective, you've basically limited your size. You can't get bigger than your supply lines will permit you to get. Think about it from an economic standpoint. For instance, my salary, which is my choice, right? I choose to teach, which basically means I take a vow of poverty. Right? I just don't have a white collar on, right? That's right. So that my choice, my salary will only allow me to afford a 15-year-old Ford Escape. Right? If I try and get the Bentley, bad things are going to happen, right? Because I don't have the resources or the strategy, the economic plan to reach that level. So what I've chosen to do, because it is easier for me, for instance, to teach science than it is for me to be a member of the Denver Broncos, then I've chosen something that's relatively easy for me to do, and I can afford what I can afford, but I can't get beyond that. Right? So I'm limited. I am what I am. You see what I am by the choices that I've made as I've actually as I answered those big biological questions of life. Okay. So now all of a sudden, we're not just answering big biological questions of life, are we? Now all of a sudden, we just upped the stakes, didn't we? Every time you make an answer, every time you answer one of those big biological questions, there's consequences to that. You want to do business this way? That's fine. You can do that. But all this stuff over here, you're going to be leaving behind because you got to pick a horse. You got to pick a horse and ride it. If you pick the quarter horse, in this case, right, then you're not going to get very far very fast, right? But you chose to pick the quarter horse because it was easier for you to get on, right? The raging stallion was too much horse and too scary. In my case, right? I'm a total city boy, right? Horses are frightening, just because they're big and powerful, but cool at the same time. So yeah, I'm on the quarter horse, right? The pony, but I'm just sort of trotting along. So in the 19th century, in a former life, I was the dude with the mule, right? I wasn't riding the horse. So I wasn't getting very far, but that's okay. So let's take a look at this diffusion concept, the rate of diffusion. Obviously, we've already talked a little bit about distance, right? So the rate of diffusion is inversely proportional to your distance. So for instance, your rate of diffusion, DR, diffusion rate, increases as your distance or your size decreases. Notice what I said. Who smells it first? Raphael, right? Because he's closer to me. So the diffusion rate is faster. It's going to him faster. But by the time it gets to Antonio, it's going to be a little slower. So it's going to take a little longer to get to him. Okay. So diffusion rate is inversely proportional to your distance. Well, let's take a look at some of these other parameters. Let's take a look at surface area. So if you have a lot of surface area, then typically it's going to increase your diffusion rate. So it's directly proportional to your surface area. The more surface you have to cross, the more you're going to get across. It's just that simple. Okay. You can kind of think of it like trying to get out of a concert where there's a crush of humanity and everybody has to get through this tiny little door. So that's not going to be very easy, is it? Because there's not a lot of surface area for you guys to fit through. Now, if instead what you did was basically take like the triple wide doors or a whole bank of doors and open them all up, you increase your surface area, which means you can get much faster diffusion. Everybody can go through that much faster. Another thing is temperature. So because molecules, basically when they're diffusing, they move faster when they're vibrating and they vibrate faster when they absorb heat, then temperature, as you increase your temperature, you're going to increase your diffusion rate. Now that's helpful, for instance, when you're trying to dissolve salt in water or sugar in water, right? Because it helps to dissolve it faster. We use that trick all the time in cooking, right? Not so helpful for us though. If we want diffusion to go faster, it's not really functional for us to just turn up the heat. Because we learned about this in the previous chapter that if you dork around with heat, you're going to start sacrificing the function of your proteins. So there's a huge drawback on that one. So probably not the best strategy for us to increase diffusion rates, but it can happen. The other one is concentration gradient. So the higher your concentration gradient, the higher your diffusion rate. Now, what does that mean? So concentration gradient is the difference between your high and your low. And so for instance, if I were to have a high concentration that's like really here, and then my low is like really, really low, then that's going to be a very steep gradient. This is going to be fast. It's gonna be a fast diffusion rate, okay? Now, as time goes on, we're gonna get change here. We're still gonna get a high over here and a relative low over here, but notice now the steepness of it is much shallower. So your gradient is not as strong. So this is not as steep a hill. So this is basically going to be a slow diffusion. And then of course, eventually what happens to all diffusion, it goes to equilibrium where both of your rates are the same. So this is none. There's no diffusion here. Okay. So now what you can do is now notice you can manipulate diffusion. How can you make diffusion go quickly? Well, we've already seen it. You can modify your distance. That will change your diffusion rate. So you can kind of geek up your diffusion rate by messing around with your distance. You can also mess around with your surface area to increase your diffusion rate. And you can also mess around with your concentration gradient. So to get the fastest diffusion rate possible, you want to do all three. Have a really steep concentration gradient to make it go fast. Have a lot of surface area to go across, so there's a lot of conduit there. There's a lot of space for you to move across at once. So you can move the entire crowd all the way out, all at the same time, right? So that's what you want. And then minimize the amount of distance that you have to do this, and you're going to get maximum diffusion rate. Your cell, by the way, any given cell is a master at manipulating all these factors. And you have to, because otherwise you're not going to get enough diffusion over short distances or even long distances in order to be able to survive for much long time. So let's dig into the first one, the surface area, because this is actually one that we see a lot in biology. And this will actually lead to structure issues. So structure function manipulations. So think about this. We've already said that in order to get more diffusion, we need more surface area, right? Surface area basically is like the working space. It's like the working surface. So if you're a cell and you want to get stuff done, it's only on your surface area that you're going to be able to do that. Doesn't matter what else you have, but you have to have a working surface, right? So for instance, in this particular case, like a desk is a perfect example. There's a lot of surface area on a desk, right? But there's only really one area that's really specifically for your surface area, your working space. This piece right here, right? Doesn't matter what's going on over here. This is not usable. I'm not going to take a piece of paper and start writing on this, right? That's not useful. It's just this piece here. So when you're a cell, what you're always trying to do is you're trying to maximize surface area while minimizing volume. So how do you do that? Well, it's kind of tough, right? But we have to kind of manipulate the cell a little bit. And so what I want to do is an experiment. I want to kind of walk you through how the cell actually does this, how it maximizes surface area and minimizes volume. So surface area for a cell, remember, this is working space. So for a cell to have lots of working space is like a benefit. So the surface area will be like a benefit. And then the volume is going to be a cost because it costs you to add more structure. So really what you can take a look and see is a cost benefit analysis, just like any kind of an economic sort of a thing, right? Think of like the get 5 for the price of 4, right? That's a perfect kind of a cost benefit analysis, okay? And this is exactly what you want to do with the cell. So what you're ultimately going for in the cell is you're going for maximum benefit for minimum cost. If you can, you're looking for 100% benefit for 0% cost. We saw that a little bit, didn't we, in the last chapter? Where did we get 100% benefit for 0% cost? Not quite. You're kind of in the right area. What? That's a good one, not quite 100%, but that's a good one. I was thinking more of an extension of that. Biological activity. What do we get for free? What? Yes. There's something we covered in the lipid section that we got for free. That was Titanic. And you probably don't remember it because it came on the heels of my discussion about musicology and music theory. What you know that? Do you guys remember?
Push and pull situation.
Push and pull of what?
I can't remember the actual term.
I think I know what you're getting at, but
Wasn't it when like the lipids like got together or the little yeah, they got together and then they formed the cell?
yes, right? And I use you guys as my phospholipid partners, right? Yeah, right. And that was basically what? Cell membrane for free, right? So that was an example of maximum benefit, minimum cost. We literally had to do nothing for that, other than perhaps the cost of making a phospholipid, right? But that's pretty minimal cost considering the amount of benefits you get. So that's kind of more like, you know, buy 25 for the cost of 2. Pretty good deal, right? So that's kind of what that one was like. But obviously we don't have that all the time. So we have to really be frugal about this. So first of all, we need working space. There's no question about that. The question is, how do we get it and minimize our costs? So this is what I want to walk us through. I want to walk us through this little example of these 2 different cells. So we have a cell here, this little guy right there. And it just has a radius. Don't worry about it. We're not going to just use like hard units. We're just going to use relative units because that's all we care about. But it has a radius, let's say, of 1 unit. And then what we're going to do is we're going to use a Texas mentality, right? You got to increase surface area, then why don't you increase the volume? Bigger, better, right? That'll work. Would you increase the surface area? Yeah, you would. So let's go ahead and do that. Let's increase the cell 10 times, a 10-fold increase in size and volume. That's cost, right? This is your cost. Now, remember, it's not just about cost. You want to also wager that against benefit, okay? So let's take a look at surface area. So 4 pi r squared, by the way, I'm not going to ask you to calculate these. So you don't have to pull out your, you know, your sphere calculations, all that sort of stuff. I'm not going to do that to you. This is just for purposes of just looking at this. So for that 1 unit, our surface area was 12.57 units. When we increased the size 10-fold, we got 1257 units. Not bad, right? A 10-fold increase in size gave us what? A 100-fold increase in surface area. So did you increase your surface area? Sure you did. Did you increase it over relatively over what you originally had? Sure, like instead of a 10 to 10, you had a 10 to 100. Not bad. All of a sudden, it's looking pretty good, isn't it? Wait, let's consider this. Let's consider the volume because it's really not just about straight line size, which is what radius is. For that straight line, you're also basically having to build in all 3 dimensions worth of the cell. So when you increase that radius, it's not just 2-dimensional increase. That would be easy. That would be a 10-fold increase in your productivity. But remember, it's a 3-dimensional increase. So it's not just radius, it's all X, Y, and Z. So you're increasing in 3 dimensions, you're increasing your cytoplasm, you're increasing your organelles, you're increasing all of that because your entire system, all 3 dimensions, is getting bigger. That's volume. So it's not just your radius that's getting bigger, it's your volume that's getting bigger. So let's take a look at this one. So your 4/3 pi r cubed is going to be your volume. So for 1 unit, you got 4.189 units. If you increase your radius 10-fold, your volume goes from 4.189 to 4189. That's a cost. So notice, it went up 1,000-fold, right? Your benefit only went up 10-fold. your cost went up 1,000-fold. So when you do the ratio, surface area to volume, what do you get? That's basically benefit relative to cost. For the 1 unit cell, it comes out to be 3. For your bright idea large cell, Texas people, it actually is 0.3. So did you get more surface area? Yeah, but you also paid more for it. So when you factor in your cost relative to what you can do with it, you actually got a bum deal. You paid more for less. You can't do business that way if you're a cell. You have to be able to get production with good with a good deal, right? Because energy is expensive, and you don't have the kind of energetic capital to be able to make these sorts of deals. Okay. This is kind of like the buy 5 for the price of 6 deal. Is anybody going for that one? You're going to buy 5 for the price of 6. Basically, you just bought 5 full price and you gave them a donation for an extra. That's basically what that is. Anybody interested in giving places like Walmart a donation? Not me either. Don't get me started on Walmart. I've been good so far this semester because I hate that black hole. I love it at the same time, right? You can't get away from it. It's just not right. It's just not right. Okay, so let's just take a look at let's take a look at our invention, our toy, right? So what is all this hubbub about the microscope? We've already played with it, right? So we kind of got some ideas of it. So obviously we know that we can make invisible cells visible. You know, most things are not visible, so they're probably less than 50 microns. That's probably where a lot of these microscopic things are. That's different. But what microscopy does, I mean, we see it as like, okay, this makes an invisible object or a microscopic object bigger, right? But what it actually does is it increases resolution. So microscopy actually increases resolution, which is the reason why you have a resolution number stamped on your objective lenses that you see on your microscopes. So what exactly is resolution? Well, what resolution basically is the ability to discern 2 points as being functionally 2 points. Now, generally speaking, for the most part, in order for us to be able to do that, they have to be about 100 micrometers apart. So you can see then if things are sub 100 micrometers, we don't see them as individual points. We see them as one. Okay. And here's an example that I like to use, just to show you what we mean by 2 point discrimination. So these 2 spots right here, can you guys tell that those are 2 points? Depends on if your glasses on or not, but assuming you had them on, easy, right? Okay, now let's move them closer together. Can you tell that those are two different points? So far, so good. Now let's move them together. Now, Ruben and Ivan, how's this looking? Those 2, can you see those as 2 distinct points? Ivan says no. How about you guys in front? Still, you can see it. Right. Notice it's getting harder. All right, let's get them closer together. Can you see those as 2 distinct points now? For some of you guys, it's starting to look more like a dash. For you guys, it actually may look like one big spot, right? That's resolution. So what we've done is we've exceeded the ability to resolve 2 different points just within the room itself. And what microscopy does then is basically puts a lens between you guys in the back and the spot, so you can see this up close. And now when you get up close, you can see it like I'm right here, right in front of it, and you can see that clearly those are 2 different points. Okay. That's basically what resolution is and what microscopes actually do. Like I said, they have to be within about 100 micrometers apart or so in order for us to be able to discern them with the naked eye. And so most of those are less than 50 micrometers, which basically means they're outside of our ability to resolve them. Okay. So a couple of things to note. We have 2 different types of microscopes. Light microscopes, which you guys have been using in lab. And ultimately, what they do is they use a resolving particle that is light. So it's a photon of light. That's why they call them light microscope. So now what this means is that you are limited by the size of your resolving particle, which is light. So what that basically means is as long as your sample is big and the photon of light is small, then the photon of light will bounce off of your sample into your eye. That's, by the way, though, how you can see images. So I can see Raphael, not because of he's right there, but because the light coming in is bouncing off and reflecting off of him and to my eyes, because he's bigger than a photon of light. So I can see all these different photons of light bouncing off of him and to my eyes, and that's what I see, and I perceive his image. However, what if my sample is actually larger than a photon of light? I mean, smaller than a photon of light. So here's my photon, and my sample is smaller. Well, all of a sudden now, when that photon hits the sample, it's just going to swallow it up, and it's not going to reflect. So it basically means this is invisible. So you can't see that one. That limits your resolution. And so light is limited that way. Now, what this basically means is then you can resolve particles down with light down to about 200 nanometers apart. Much better than the 100 micrometers that we have with visible, right? So that's much, much better. However, still not good enough. So what we really want to know is what are these tiny little structures, right? And you saw some of that, right? So some of you guys may have looked and seen things like amoeba or something like that, and you see what looks like a cell with like little bubbles in it. You don't know what those bubbles are. You know they're organelles, but you don't know what they are. So what if we got a closer look at those organelles? That'd be awesome, right? Well, guess what? You can't do that with light, but you can do it with electrons. So here your resolving particle, instead of being a photon of light, is the electron. Now, how big is an electron? Yeah, vanishingly small, right? Is anything smaller than an electron? No. So is there any sample that you can put on there that's going to be limited in terms of your ability to see it? So you can basically put organelles on there, right? That are smaller than 200 nanometers, and you can still see them. Why? Because the electron will always, so here's your organelle, will always be able to bounce off that because there's nothing smaller than an electron. I always get this question from students. It's an interesting question. An electron is vanishingly small. I think I clearly remember you saying in chapter 2 that of the 3 major subatomic particles, the electrons were vanishingly small, smaller even than a proton. So can I put a proton on the slide and bounce an electron off the proton and see how you see a proton? Theoretically, yes. In reality, no. The reason why you can't look at subatomic particles with electrons in electron microscopy is because at some point when you get really, really small and tiny, like down, it's usually like around the macromolecule level, like you can probably see something like a DNA or a protein or something like that, but you're not going to be able to see like individual types of things with electrons. And the reason is because once you start getting down to a level of size, you start to you start to go into this really, really weird world of quantum mechanics. And quantum mechanics has all sorts of weird, like Alice in Wonderland types of properties that happen that we're still scratching our heads over. We're not quite sure how that works exactly, but just like weird, crazy things happen to that quantum mechanics level, which is the reason why we can't really rely on that to see protons with. But above that, quantum mechanics switches to relativity, which drives the rest of it. And this is actually something that physicists have been banging their heads against the wall for generations now. This consumed Einstein. This destroyed Einstein, actually, because we just couldn't figure out how on a little micro scale, subatomic scale, you have the world driven by quantum mechanics, and how that on a macro scale turns into relativity, because all of that, the way we think is like, well, what you have on the micro scale, like subatomic, should kind of be able to scale up, or at least additively predict the relative, and it's like completely different. So it's almost like a cocoon, sort of a caterpillar sort of thing. It's almost like you have this sort of caterpillar-like world of mechanics, of quantum mechanics at the subatomic level and the particle physics level, that just has all these weird, wonky rules and phenomena associated with them we just can't figure out. And then at some point before, as it kind of starts to get a little bit bigger, it just kind of goes through this almost like metamorphic like switch, just something completely different, very similar to like this gross looking, disgusting worm turns into this beautiful butterfly. It's like this gross looking, disgusting paradox of a thing, quantum mechanics, that nobody can figure out or predict, almost turns into this magnificently elegant and beautiful relativity that governs the rest of the universe in an elegant fashion that's super predictive, and that we have like theoretical physics, mathematical physics that can predict like well beyond our capacity to measure. It's so predictive in value, and we don't know how that works. Like, what's in the cocoon, right? Right? How does that work? It's really a fascinating thing. But that's the reason why you can't go back and see a proton, is because quantum mechanics takes over, and then you're beyond the looking glass, literally, at that point. And nothing is what you think it is. Up is down, down is up, side is right. I mean, exactly, right? So it's just all craziness. So that's kind of what that is. But the nice thing about it is, if you stay relatively large, organelles, for instance, is about as small as we get, then you can basically drive that resolution down to about 0.2 nanometers. Not too bad, right? So that's what, about 1,000-fold increase in resolution? Not too shabby. All right, and that does a lot for us. We have actually, for electron microscopes, which basically kind of invented around the 50s, 60s, so they haven't been around for a long time, but they've been revolutionary. So like, for instance, our current conception and realization of the way cellular structure works has largely, hugely been the beneficiary of this particular instrument. And so it's allowed us to really be able to visually see and piece together exactly how these organelles are, how they're structured, how they work. It's been really a massive, massive tool for us. There's two different types of electron microscopy. There's transmission, which basically will take a sample that you put like on a slide, and it'll beam electrons through that sample. Very similar to like a cross section, where it kind of beams through, and you kind of get some resolution through a detector. So you have some sort of a detector here that that kind of accepts whatever that output is. And then you have a scanning, and a scanning basically will essentially beam those electrons on the surface of an organism. So here's my organism, and the electrons will basically glance off of the surface. And what it'll do is it'll give you a three-dimensional kind of a topographical map of the surface of that organism. We see both of these actually in biology quite a bit. And if you're wondering where our electron microscopes are, where our electron microscope lab is, we don't have these. These things probably cost hundreds of thousands of dollars. So Boulder has one, Anschutz has one. I don't know if Denver has one. If they do, it's probably in the basement, and it's probably limited. I don't think they actually do have one, because this is just, you usually have to have a pretty healthy cohort of cell biologists to be able to justify an electron microscope. And that's true for Anschutz. That'd be true for Boulder. I don't think it's true for anybody upstairs. There's just not enough of it. And besides, it's easy enough to just send your samples to Anschutz and just have them run it. So because once you start to get equipment like this, you don't just have some undergrad tech running it. You've got basically hired people whose job it is to take samples from the lab and to run them, to take care of the machine, to process the data, and they give you the data. You never actually get to see the machine or touch it. That's usually how these sorts of things work. I don't know, you want to get this piece right here, right? Okay.
The first one is the rule.
Yep.
Because I've seen kind of different use of those. It's like a grayish picture.
Mhm. Yep, they're grayish. Sometimes they're colorized, but it looks like you're looking at a cross section of it that looks similar to what you would see under a light microscope, where it's a kind of a transfer through a cross section of it.
3D printed thing.
Now, when it looks like a three-dimensional, like you're looking at the surface of it, that's the scanning. That's the second one. Yep. Kind of creates almost like a topographical map. That's the scanning electron micrograph. So they're both very helpful. So this is kind of your range, right? So basically, here's your visible range. You can see actually quite good to be quite in terms of like how much you can see. But then you get to your light microscope, which is right here, overlaps with your electron microscope, which all goes all the way down to here. So you notice you technically can get down to amino acids, but we just don't because the resolution starts to get a little weird down there. So generally speaking, we're probably looking at large protein macromolecules at best, probably from here up. So they got to be large protein complexes to be able to see them. So this is kind of what it looks like in terms of our naked eye. Now I like this one because it shows you examples of what these are. So the first one is going to be bright field. This is basically your normal light microscopy. This is what you guys have been doing, right? So basically light beams through the specimen and then you kind of see the translucence of it, right? And notice you can see all these little bubbles in there. You don't know what they are, but you know they're organelles of some sort. The other one that we used to have this actually in the lab. Somebody took off with it somewhere. I don't know what happened to it, but we used to have dark field. Dark field is different in the sense that it has the condenser component, right? That scatters light. What it has instead of the condenser is it has like a dark area that like the entire condenser is darkened black. And it's got like a little ring where the light shines through it. And so the specimens, that light will just go through the specimen, but it'll block out everything else. So all the background is black. So it looks kind of like this radiant image of a specimen on a black background. Really, really cool because it brings out a lot of nuances of structure, especially I noticed that the organelles. Notice now you're able to see much more detail in what are going on in those organelles now. So very cool, very nifty. I want to get that condenser back. We also have phase contrast, which is another type of light microscopy. These are all light microscopy, just different types of ways you're manipulating light. That's all these are. Phase contrast, which we do actually have a microscope with phase contrast in it. But this is one where you use the wave particles of light instead of the photon, the particle nature of light. And you essentially, like if you take a look at the waves, you know, like if a wave matches up to each other, crest to crest, then you get an amplification of that light. But if they cancel each other out, if they measure up crest to trough, and so you can have these cancellations of wave. And so this phase contrast is basically manipulating the wave properties of light to kind of create these weird little contrasts and shadow plays on the organism itself. So you can see it's kind of like a slight modification of what you see with bright field, which is normal. But in some cases, you can actually make the phase contrast look similar to dark field. And so it's really cool. The last of the light microscopes is what's called DIC or Nomarsky. This is differential interference. So this is basically where you get interference of light waves with each other. So they interfere with each other, and that just creates a slightly different kind of a nuance. It creates this sort of bas relief look of a cell in addition, or like overlaid on top of like the normal light microscope. It's one of my favorites actually. But it's the same thing. It's a light microscope. You just have a different set of optics in there to kind of make this sort of an effect. Now, since we are at our witching hour, of course, right, just when we're getting ready to have fun, we'll start off actually on Wednesday having more fun. Only now it's like really getting fun. So I'm going to put here, start here. That's my start here button. Right. And because we just finished up all the light microscopes, now we're going to move into the fluorescence microscope, slightly different, and then we're going to talk about the electron microscopes.